Today, we're going to tell you something about how to program the AURIX MCU in a parallel fashion. There will also be something on safety aspects, but all the heavy lifting today will be done by my colleague, Michael Rückauer, who will do the presentation. I'm just here to support him a little bit. Michael, if we go to the next slide. Yeah, there we are. Just let me briefly tell you who we are and what we do. MTrix Technology is a still fairly young company. We're sort of coming towards the 5-year watermark, yeah, so we can still probably be called a young company. Here, partly due to the current situation, you see part of the team. This is now quite an old photo. So we've managed to grow the company in difficult times. We're roughly 15 people now. We are concentrating on software tools, mostly in the, let's say, analysis and acceleration area. So we've got 2 products, the MTrix Parallel Studio. This is our main product, which provides a whole suite of solutions, and part of that suite is the MTrix Code Generator, which, as the name suggests, concentrates on generating code from mostly model-based input. Yeah. The company provides a number of services, all to do with what we do, what our focus is really. Yeah? So if you need some project consulting in the sense that you're looking for some more powerful hardware, then we can probably help you with this. We provide a number of trainings, starting from some fairly generic things to some specific training on your first project, for example. And generally for bigger customers or technology partners, we can provide workflow integration and tool customization. Now, I don't want to take too much of your time, which is, as far as I remember, why I can now more or less hand over to Michael. Is that correct, Michael?
Yeah, thank you, Rainer, and
okay,
thank
great.
you everybody for joining the webinar today. So what I will mainly tell you is our experience in parallelizing a control application for the Infineon AURIX microcontroller. And so I will start with a little introduction, why use multi-core microcontrollers, tell you a little bit about the MTrix parallelization workflow, then go into the main part, which is the parallelization of the customer control application and the difficulties and we had there and how we solved them. And then I will also tell you something about how we ensure the functional safety of our generated code. So the first part there is, so why do you use multi-core controllers? So modern embedded systems, like modern cars, are equipped with more and more complex functions. And this leads to an increasing demand on their processing powers. So, and why also you need to fulfill real-time requirements and maintain low power consumption because of battery reason, and also because you have to take care of the cooling and these things. Yeah, and the solution for that are safety certified multi-core microcontrollers. So they have multiple processor cores, so they achieve a speed up by calculating several tasks in parallel. So, and this may also lead to more efficient processing with reduced power consumption. So you don't have to increase the clock frequency to very high levels, which increases the power consumption by a lot. Instead of that, you distribute your computations to multiple microcontrollers. And safety there is usually achieved through isolation, redundancy, and checking the correct function of the cores during runtime. And one prime example for a multicore microcontroller is the Infineon 32-bit TriCore AURIX MCU, which is widely used in safety critical applications, for example, in automotive. And so if you look at the structure of the system, if you take a look at a single core, so it will have integrated code and data memory, which can execute code in a very fast fashion. Then from there, you have an external code and data memory, which is also very close to the core, with a little bit higher latency for access. And if you now look at the first 4 cores of the system, you can see that these 4 cores, they can communicate with each other through these memories. But here it really depends, that the code execution time really depends on where the code is located. So if a core can access its own memory, it's much faster than if it has to access memory that is external or mapped to a different core. So, and there are also shared external memories. And in the case of the AURIX MCU, which has up to 6 cores, you will also have, let's say, a separation of 4 and 2 cores, and there are more interactions to be taken account if you, for example, want to access core 4 from core 0. And it even gets more complicated if you want to target external memory. So the system is certified for building ASIL-D systems according to ISO 26262. Also, because you can run different applications on different cores, and because of the memory architecture, you can actually isolate functionalities that are running on different cores from each other. So what this should also already show you that there are a lot of decisions to take if you want to effectively utilize such a powerful multi-core microcontroller. So we have parallel hardware, and if you don't use any parallelism, especially for the Infineon AURIX, you will not gain a lot of performance across the generations of the AURIX. So the first generation AURIX, it has 3 cores, AURIX TC3xx, it has 6 cores, and the new version that is going to be released, I think, sometimes in 2022, if I'm not mistaken, it will also have some special function accelerator that needs to be programmed completely differently from what you know from the other cores of the AURIX. So, but the problem there is if you don't, because the clock frequency don't scale too much, there's not too much change in the microarchitecture. You will not gain a lot of performance advantage if you don't use parallelism. So even in the first generation, you will achieve high speed up if you use all the available cores. But with each new generation, the speed up you will achieve compared to no parallelism will become larger and larger. So it's very important to actually distribute your application to these cores in order to harness the full potential of the AURIX architecture. So what you can say there is parallel hardware needs parallel software. So, and the question there is, how do we actually program for such an architecture? And the offering we are making is the MTrix parallelization workflow. So if you look at our workflow, so our two main products are the MTrix Code Generator and MTrix Parallel Studio. So in our flow, you can actually start from different input models or programming languages. You can start from Simulink models or from MATLAB code, but you can also start from C code. And in the first step, what we do is we generate sequential C code from the Simulink models or the MATLAB script, which will then, in a second step, be parallelized by MTrix Parallel Studio. So we take the generated C code and turn it into parallel code that hopefully has a much better runtime than the initial C code. And our solution then allows you to deploy the parallel C code to different target architectures. So it's different kinds of multicore CPUs. What we support, for example, are ARM-based CPUs, the Infineon AURIX, also PowerPC, TI DSP. So there are a lot of CPU architectures that we support, but also what we want to target are also special function accelerators like GPUs or FPGA, or also the special function part that will be in the next generation of the AURIX. So, and our workflow actually is in some way automatic. So it's some kind of automatic parallelization, but it's a parallelization that allows the user to interact with the parallelization and stay in control what happens during parallelization. And so the developer decides what to do regarding parallelization of the code. So in the first step to this is the analyze step. So in order to be able to actually do any parallelization, you first need to get a feeling for your program. So where does the time go? Where do you need to parallelize to achieve a significant speed up? And for that, I will just show you in our software. I will show you a little example. Where is it? So here you can see our software, and on the left side you can see the workflow. So you have the active project, and the current platform we're targeting with this project is the TC3xx starter kit, so AURIX second generation 6-core. And so this workflow actually reflects the workflow I just showed you. And so the first part is the sequential C code generation. And in this case, we will start with a Simulink model. So we import the Simulink model from MATLAB actually. And so what you can see is just a viewer. So it's not something where you can edit things. It's just where you can see the model. You can go inside the model and so on. And the first step, as I said, is actually running code generation. So this is after this tool has run, you will be able to see the generated output code. So which is given here. So it has information on tracking back where the original code comes from in the model, for example, with these statements. So you can track, okay, the code generator generated code from this part of the model. And as I said, the first step for you would be the analyze step, which actually analyzes the code and shows you where it is worthwhile to parallelize your program. So, and what you can see here is a view of the whole program. So if you go up, you go deeper into parts of the program. So the block down there, the main block is the whole program. And for example, if you drill down here, you will get to this convolution, which actually corresponds to this one. And there's another one. This one actually corresponds to this. And what you can see is that these two blocks take the most time. And this is actually where you want to parallelize the code. So, so I will go back to my presentation now. And the second step is actually to optimize. So to improve the code. So what if you go here, what our tool shows is actually so it already did a parallelization, and it gives you a suggestion where to parallelize, and as oh, I haven't told you that on the horizontal scale you can see the runtime of the program, and you can see that those two will consume the most time. And if you now look at the parallelization view, you can see, oh, we use 2 cores of the 6-core AURIX, and those 2 parts, they take the most time, and also they have been parallelized. But this is not ideal for a 6-core CPU. So we have an optimization step where the developer can decide which transformations to apply to actually improve the code, the parallelization of the code on the target. So in this case, we have large for loops, because this is actually an image processing application. And what we can do, we can apply transformations to it. And what I will do here is I will actually split each of those loops into 3 loops. So, and if I do that, I apply those changes, and it will run the whole tool chain again. And after it is done, you will automatically see how it changed the parallelization. So if I now take a look at this, so you can see on top that it actually made 3 loops out of the single loop we had in the beginning. And you can also see that the tool already mapped those loops onto the 6 cores, which yields a speed up of 3.5 compared to the 1.8 we got before we did the transformation. So then, okay, parallelize is already done by our tool, and also there the user can adjust the parallelization. For example, you can pin certain tasks to certain cores. You can say that certain tasks shouldn't be parallelized, or that they should only be parallelized for a subset of the cores. These are things that you can decide there. And then you will you can check the results. So you will see in the in our parallelization view, or in our schedule, the expected speed up. And if you're not satisfied with the results, you will go back, and what I did, I changed. I found out that I would like to parallelize the loops, and then I applied those new settings and checked the results again, and saw that I have a better parallelization then. And in the end, what you can get, but you can also do this during the development process to measure the time on hardware, is deploy the code to the system. So if you look at the parallel code here, this is the parallel code actually for the 6 cores. So part of what you can see here is work we did to actually deal with the different memories of the AURIX I showed you earlier. So this is actually a mapping of data and functions to different memory sections. And what you can see here is this EMX API send, and there are also EMX API receive calls. This is actually the parallelization, the communication, the synchronization we insert into the code, into the parallel code we generate to actually have a parallel program. So the developer doesn't have to do anything. It's just the tool will generate optimized code for the target architecture that will have all the synchronization and communication inserted automatically. So already showed you MTrix Parallel Studio. On the left side, the workflow. On top, you can see the input model, and on the bottom, you can see, okay, this is where the program takes the time. And on the bottom, you can actually see the parallelization result. Yeah, so this is was a short introduction of our tools. And yeah, I will now go into parallelization of our sample application. So what I showed you now as an example was actually an image processing application, which is rather different from what I will be showing you right now, because for our image processing application, it was quite simple to actually identify which parts of the program occupy most of the time. So there's actually a single block or a few blocks that take most of the time. This you usually won't have for controlled application. And one application we did for a customer is a control application modeled in Simulink with a short overall runtime, a large amount of short running tasks. So you can see that in the image on the bottom. So there's not a single large block to identify, but there are many blocks that have similar size. So it's not easy to see where actually to parallelize. So this is also something we can do in our tool, but the approach to do that is a little bit different. So it's still the usual approach, but there are a few things that have to be done differently, because especially in these applications, the effect of communication is pretty high. So if you look at the example, so these are some tasks. The arrows represent dependencies between tasks, and if you schedule this sequentially, you will have, let's say, the block length, the approximate runtime of these tasks. And so here I have a parallel schedule, and well, you could say, wow, it's good. Runtime is decreased by 35% when running in parallel. But unfortunately, if we don't take the cost of data transfer into account, which is pretty important if in control applications where tasks are short and every data transfer between cores or also synchronization between cores will add to the runtime a lot. If you don't take that into account, you will not achieve the runtime reduction you want to achieve, but the synchronization communication overhead might be significant, and you might even get a runtime that is lower than the sequential case. So the workflow we provide for these kinds of applications is this. So what I said, the challenges are a huge performance impact of communication. So what we need to take into account are both accurate task runtimes and also take into account communication costs, especially for a smaller transfer, which occurred in this example. We have a lot. And and also what you usually try to do, what we try to do in the image processing case, we actually wanted to divide tasks so that we have more tasks that we can split onto processors. But if we have 1,400 tasks, we really want to group tasks together so that we don't have too many short-running tasks that we can schedule to different cores. So it's, in that case, it's quite the opposite what we try to do. So and a very important part is the performance estimation. So if you look at typical programs, a rule of thumb is that 80% of time is spent on 20% of the code. And you should focus on optimizing and parallelizing the code that matters. So which is what we saw in the image processing example. So we could readily identify which parts we should optimize. But a solid understanding of task runtimes is vital for good parallelization results, not only for the developer, but also for the parallelization tool. And this shows a lot more for the control applications we have here. It's not that much of an issue for the image processing application. Because if you look at an example, we have 4 tasks with estimated runtimes that correspond to the block width, and also a schedule, which in that case looks pretty ideal. But if, for example, on hardware, task A takes longer than expected, task B takes shorter and than expected, also task C, then we will have a gap in our schedule. And in that case, this is wasted only because we have misestimated the task runtimes. Therefore, the question would be, what kind of performance estimation methods can and should be used for finding out where the runtime of the program goes? So that the simplest case, which I showed you in the first example with Parallel Studio, is the static code analysis. And there the estimation is based on the input code and an abstract hardware model. So actually it is not, for in our case, it is based on the C code and not actually on the code, how it is run on the target. And then there is simulation. So what you can do is actually use a simulator. It must be a cycle approximate or cycle accurate simulation of the hardware. Trace the simulation and assign the tasks the runtimes that are calculated by the simulator. Then there's also profiling. So there you run the code on the hardware and you inject some code into the program that measures the time on hardware. And then there's hardware tracing. So you actually use an external debugger and the hardware trace unit to observe the execution closely on the hardware, which is the most accurate method. So now the question would be, what kind of performance estimation did we use for our sample application? as I said, the challenge here is that communication costs are close to task runtimes. And the observation was, when we parallelized this for the customer, was that overestimation of task runtimes led to bad parallelization. So we first tried a static code analysis, which is default in our tool and usually is enough for, let's say, image processing applications. And the problem there is that loops dominate task runtimes. So most loops can be unrolled and optimized out by the compiler. But as we are working on C level there, the compiler optimizations are not considered, and therefore the task runtimes are vastly overestimated, which led to bad parallelization. So poor results for this one. So we tried the simulation with the TriCore simulator. This is actually something, if you have a good simulator, this is a very good approach because you don't need to have any hardware and you don't have any overheads from profiling the code. But in our case, the problem was that it overestimated the times for branches and memory accesses. Therefore, we also got poor results with that. So what we did is we actually did profiling on the target system, and there our tool also has the possibility to auto-generate profiling code. And what needs to be considered there is that you have limited hardware resources, and which will be used by your profiling data, because the profiling data has to be stored on the system during runtime of the application. During runtime, you will have extra functions you need to call for the time taking and stuff. So this is actually something that needs to be applied carefully, because if you add too much profiling code, your application runtime will not correspond to the one you would get without profiling. And in our case, this worked pretty good. So this is actually what we chose for that sample application. Yeah, and then, so after getting those performance numbers, the next thing is actually do the parallelization. And as I already said, regarding task clustering, you usually try to increase the number of tasks considered for parallelization, but for control applications that has many tasks with short runtimes, this is not the way to go. Therefore, it's better to actually cluster those tasks and reduce their number. So, which means that we take several tasks where we analyze beforehand that it will not make too much sense to move them to different cores, and treat them as a single task. So let's say what we did, we reduced the 1,400 tasks to 100 tasks that are then fed to the scheduler. So actually always, so in on average, 14 tasks mapped to a single task to actually be able to tackling the scheduling problem in that case. Okay, it's actually, I was wrong there. It's we reduced it to 50, not 100, but this is actually something that is selectable in the tool. So it actually depends on, it's actually a trade-off you do. So how much clustering you do, because clustering might reduce the quality of the parallelization in the end, but decrease the runtime. So it's actually a trade-off. If you just want to have a first estimation, you do a more strict clustering, and so if you want to have a good results, you will reduce the clustering a little bit. And the next thing is actually assigning the task to processor cores, and this determines when and where tasks are to be executed. What you need to do is actually to consider task run times and communication times. So what you can see here is actually a distribution of the code, and what we want to achieve is actually to minimize the total runtime. This was the case for these kinds of applications. There might be other optimization tasks, always fulfill task deadlines, or minimize response time, and it depends on the actual application. But for these application, the goal was to minimize the total runtime of the control algorithm. And so this is an optimization problem that can be solved using exact methods, for example, like integer linear programming, or also by heuristics. And in the case of that application, we used heuristics that work together with the simulated annealing approach that allowed us to accept worse solutions, worse temporary solutions, in order to get a better global solution. And for this kind of problem, this worked pretty well. So, and now that the actual parallelization is done, so we know the how we want to map the tasks to the different cores. But what we haven't done yet is actually generate any code for the target system. And so what I should make clear again is that in our approach, the developer doesn't do any manual parallelization. So every thing from dividing the program into different parts for the different processors, and also doing the communication and synchronization is done by our tool. And as our tool, as I said, parallel execution requires data exchange and synchronization. You have to decide when and where to communicate, and wrong placement is a common cause of execution errors, like deadlocks, where the program execution, where the cores wait for each other without ever being able to advance, or race conditions in general, where the execution order of code on the different cores defines the outcome of the program, which also shouldn't be. So as I said, with race condition, the occurrence of errors depends on execution timing. So also, it is not guaranteed that these errors appear with every execution, and therefore it's very hard to debug. So because if you apply breakpoints or debugging actions, they also affect the timing of the code, and you might not observe these errors when you try to debug them. And also because of this, correctness of synchronization is hard to prove. That's why, as I already said, synchronization in MTrix Parallel Studio is handled automatically. We use a systematic approach that ensures that no race conditions can occur, and also no deadlocks. And so, as I already showed you in the demo at the beginning, explicit communication instructions can be found in the generated code, which you can see here. It's this Emacs API send or Emacs API wait. The question would be, how do we actually implement these API calls that we have there? So this really depends on the kind of architecture we have. For example, if you have a standard Linux system with ARM cores, for example, you could just use, or we can just use the pthread implementation or MPI, for example. We have back-end implementations for these. Or if you're in an AUTOSAR context, you would probably use the mechanism that AUTOSAR provides. For this application, and because of the complex infrastructure of the AURIX, memory infrastructure of the AURIX, we did a custom communication implementation for it, and so we had to decide where to actually place the buffers for these things. And yeah, because placement of shared data structure is critical for performance in a system that has so many options to place code and data with different access latencies. So the question was, where should the shared data be placed? We won't place it in code memory because it's read-only and it's only for writing code. Then it should be put in low latency memory. So that means any external memory is out of the question. Also in memory with minimal sharing, which means that the shared memories are out of the question. And it should be local to the core. There it is important that received data, so that core that the data receives from another core that is to be used by the core, then it might be accessed multiple times. So it should be pretty close to the processor. So if, for example, if you're here, core 4 wants to access these data, it should be local to its memory, either there or there. And the data that is sent by another core, it should be sent to the receiving core through the interface and put there. So that this is usually a one-time thing. You send the data from core 5 to core 4 once over the bus, and then core 4 can use it multiple times, and it does not interfere with anything else during this accesses. Therefore, this is how we implemented it. Now I will come to the target platform specification. So how we actually do this. So we do not only target AURIX in our tools. As I said, we're trying to target lots of different hardware devices, and our tools should be able to work with any of these. May it be an ARM, or may it be an AURIX, or may it be a PowerPC or TI DSP or whatever. So because of that and the properties that the applications we try to parallelize have, accurate modeling of both hardware and software is crucial for good parallelization. And also the generated parallel code needs to integrate into existing software. So if you have a piece of software, you usually don't have a main, and it runs from there. It has to integrate into an operating system, into some sort of framework or base software. It needs to call initialization code that is target specific. For example, from the AUTOSAR microcontroller abstraction layer, it is to interact with base software, may it be Linux API, an RTOS, or also the AUTOSAR based software. And it also needs to interact with platform APIs, for example, POSIX in the case of Linux, or MPI, or also with the AUTOSAR RTE. So this needs to be specified somewhere. Yeah, and the question would be, how does the parallelization software get this information? And so our approach is a comprehensive description of hardware and software properties. So as I said, we include many target platforms like Infineon AURIX, first generation, second generation, ARM Cortex-A, Texas Instruments DSP, PowerPC. So, and it's also possible to add additional platforms not with a small effort. As I said, target platforms can be created or adapted by the user. They also can be changed on the fly. So if you're in a project and you want to target another architecture, you can just go into settings and select a different target architecture. And and these target architecture or target platforms, they are specified in a platform description, so which describes the software, so which APIs are available, which communication API is used, which libraries are there, which software frameworks, and then there's also hardware descriptions. So what kind of processor do we have? What is its microarchitecture? How many cores does it have? What memories are there? What are the clock frequencies? And a very important part, the most important part actually, is performance data. So there's performance info on instruction timings, which you can see here. It's different kinds of operations like 16-bit addition or 32-bit addition, and the performance data here, it's given in clock cycles. So what is actually the latency and throughput of those instructions. And then also we have communication costs. So communication costs between different cores of the CPU. So it always depends on the API implementation. So here it is our specialized ring buffer implementation of the AURIX, and so you can see it's always pairs of a source and target in that case. So from one TriCore AURIX TriCore to another, you will get a cost table. There's a cost table that gives the costs of communication depending on its size. And yeah, so the target platform we used for the sample application is a TC397 or AURIX 2G starter kit using the biphases framework with the Infineon low-level driver, no operating system. So this is pretty bare metal, and a custom communication implementation. But you may also, you may also specify in the target platform, as I said, different operating systems like Linux, or if you use AutoSAR, or this is all possible. Yeah, now I will come to the results of what we achieved for the parallelization of our customer control application. So the application was mapped to 2 cores of the AURIX TC397 system. So it didn't make sense to use all of the 6 cores. So we achieved the best parallelization actually with 2 cores. Using more cores didn't yield a further reduction of runtime, or not by a margin that actually would make it worthwhile to have an additional core. So parallel runtime on 2 cores was 55 microseconds, which yields a runtime decrease of 29%. So for a control application with such a short runtime and these many tasks, this is actually a very good result. So usually for control applications, you won't see that much of a linear performance increase as you would see with image processing, because you have large chunks that can operate in Solid, and here you have a lot of interaction between short tasks. So achieving a runtime reduction of 29% was actually quite good. This was achieved with MTrix Parallel Studio with comprehensive hardware and software modeling. What we had to do was to do accurate performance estimation through profiling. We did that task clustering and scheduling, and used a custom optimized communication implementation that was optimized for word size transfers. We had a lot in this application. Yeah, and so this is the setup where we actually tested the application. So we used a debugger, and what you can do in MTrix Parallel Studio, you can automatically instrument the source code for profiling on hardware, deploy the parallel software to hardware, also using MTrix Parallel Studio, and then acquire the profiling results automatically, also to be displayed and used within MTrix Parallel Studio for further optimization. So now that I'm almost done. So, but as our talk is actually about safety critical software, I need to have a few words about how we actually guarantee the functional safety of our generated code. So the code that we derive from the sequential input code is derived through a series of transformations. So as I said, there are no manual edits allowed by the developer, and every step we do is traceable and also repeatable if necessary. So with this programmatic approach, we guarantee that there are no race conditions, no deadlocks. So the systematic approach of EPS leads to correct by design parallelization. Okay, then you might ask, okay, he can tell us that, but how do they verify that it is like this? And this is what we do with our functional safety workflow. So what we do is we do not qualify the tool itself, but what we do is we compare the input code and the parallel C code. So we actually do a formal verification using our MTrix safety kit, so that we can be certain that the parallel code is actually does the same as the input sequential code. So yeah, and this is done with a formal equivalence check. And how this is done is actually we are matching the structure of the program. So if you look at the left side, you see the sequential part of the program, and if you look on the right side, you see the parallel part of the program distributed to two processors. And so the gray parts are actually essentially the same. And what we do is we actually match parts of the code. So it's pretty easy for this one. For this one, it's also just a rename of the variable, so still equivalent code. Here it's a little bit more complicated. So in the sequential code, we had a while loop, which we transformed into a for loop. So we need to match those two, the while and plus I2 to the for loop to actually match equivalence. And then it gets a little bit more complicated, because that B is actually transferred between processors. So you see that the functions are different. So the function equivalent of the sequential function that is matched to P0 only has the array A, and the one on processor 1 has the B. And the question would be how do you transfer the data between those two, which is necessary to do the calculation. So here, so the B is located on processor 1. So we match the sequential part to the part mapped to processor 1. So this is actually the same. So the next one is actually not there in the parallel code, not directly, because it's on processor 0, not processor 1. So we actually need to have a path to move B from processor 1 to processor 0, which you can see here. So the B1 will be sent to processor 0 with the EMX API send. So there's communication. And then you will actually have a mapping of line 14 on sequential code to line 13 on processor 0 parallel code. So, and all these together, those 3 lines on the right side actually yield the single line on the left. So, and with that, so this is a little bit of a simplification, but our tool, this is essentially what our tool does to actually verify that each line in the parallel code maps to corresponding lines in the sequential codes, and then to actually achieve a formal verification that they are actually the same, so that they are functionally equivalent. So then one word about AUTOSAR. So at the moment, our product does not directly support AUTOSAR, but we are working on an AUTOSAR implementation, which is supposed to be released in the second quarter of 2021. So the idea there is actually you usually have your AUTOSAR authoring tool, might be from ETAS or another vendor, whatever you prefer. And we take, import and analyze the AUTOSAR model from the AUTOSAR authoring tool. So we read the system configuration and the software component descriptions from the AUTOSAR XML, import it into MTrix Parallel Studio. We also support black box software components and runnables. So even if you don't know the implementation of the runnables, if we know how they interact and their runtimes, we can parallelize. So then we would do the parallelization the same way as I showed to you. We wouldn't then not directly generate target code, but we would actually export the results we have there back to the authoring tool with updated software component descriptions that reflect the new core mapping, also the base software partitions as we created them. And this all takes into account the AUTOSAR system model, the hardware properties, the properties of the RTE and the base software, like, for example, the communication performance. This outlook actually concludes my talk on parallelization for Infineon AURIX. Thank you very much for attending.